When I was a little girl, we used to play this game. It was called marbles. Old-fashioned, but we loved it. We loved taking marbles outside and playing with them. And one day while we were outside, we were writing our scores down on a paper while we were playing, and a little bit of wind picked up and the paper kind of floated away, and we all went scampering after it. And we caught this paper and we brought it back to where our marbles were, and we noticed that the marbles hadn't moved at all. And that got our little minds curious, and so we decided to do this little experiment, and we got up on our porch and started dropping marbles and pieces of paper from our deck. And we noticed that they didn't exactly react the same. So, why is it that when you drop a marble, it falls straight down really quickly, but when you drop a piece of paper, it takes several seconds to float to the ground? It's because of gravity. Gravity affects everybody. Society literally depends on gravity. Going through all of this, we're all sitting here. We are depending on that gravity to keep us tied down to the earth, so we don't float away. Now, I have been to UVU for a few months now, and I'm trying to go back, trying to finish my degree, get it done fairly quickly, and in the process I had to take science classes, and I became fascinated with these string theories and quantum physics and things like that in my science classes. And it's fascinating to look everything up and to see what people's thoughts are on it and the process, because it's been this continual argument for years. Now, going back, we learn about gravity, but they don't tell you everything. You grow up learning about gravity and how gravity is a force. Yes, it affects everybody. I mean, it's always there. It's always acting on us. But guess what? Gravity is not a force at all. So, I'm going to discuss the fundamentals of gravity. So what causes it, how we discovered it, how we know, like contrary to popular belief, how we know that it isn't a force. So we are going to revisit some history here. Back in 1687, Isaac Newton wrote this thing on physics, and it's called Philosophiae Naturalis Principia Mathematica. And he had this equation for force. So force equals gm1 m2 over r2. Simple speech is two objects with a mass exert gravity on each other in relation to their size and the distance. So think of it like the sun and the earth. Big ball of fire, little ball of earth going around the sun. So they are based on gravity. Earth is tied to the sun. We can't get away because of the gravity. Now, fast forward a little bit to Galileo. He stated that all physical laws are the same in every inertial reference frame. So, simplifying that, motion is constant. All events are pretty much invariable, and the physics is always going to be the same. So, we have these two people that have theories out there. Okay, different time frames, but they're going to connect. Fast forward, we have an equation for how gravity behaved and how large objects somehow pulled on these small objects. We just didn't know how at that time point. We are going to fast forward again 200 years, where James Maxwell stated that the speed of light is constant, regardless of reference frames. So this seems to be contradicting, right? So an example would be a plane. So you see a plane in the sky and you see the lights blink, like boop, 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 as it flies. Whereas when this plane is on the ground, they blink at the same time. So, rewind, which is right? Which one of these guys is right? reference frames or speed of light? Well, we're going to add another portion to this. Enter Albert Einstein. He says that the speed of light is always the same. Now, if a jet is flying at 100 miles per hour, the speed of light is going to be 2.988 10 to the 8th. It's always going to be that. But Galileo said speed is relative. Maxwell said not. How is this possible? Well, both are right. We've been wrong about everything else. Enter space-time. Everybody thinks about space-time continuum, all these geeky things come up. Well, space and time are said to be one and the same. One person's space is another space and time. Vice versa. So, that actually contradicts Newton's theory of gravity, if you think about it, because gravity is generated by mass, and mass cannot travel at infinite speed. So how can objects be acted on instantly by gravity? If one argues gravity is simply an energy force, the energy must have mass. So, what is gravity? Gravity is not a force. It is simply an acceleration. There's a thing called the principle of equivalence. I will not go into that, but it has an amazing outline of why this is. Why is gravity not a force? It is that acceleration. So, for example, take a plane taking off. Plane has a whole bunch of luggage in the cargo hold, right? The luggage kind of falls back when the plane takes off. What's causing the luggage to fall back when the plane flies? Well, it's gravity generated by the plane. And the objects move. So when the objects move, they get shorter as velocity increases and disappears into the speed of light. Now that's kind of a abstract idea, and we aren't going to dig into that whole. But another example is clocks. That might be a little easier to explain, is the clocks. They tick, 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 until they slow down and then they stop. Another example is mass increases to an infinite speed of light. So, what does that mean? A moving object gets shorter, velocity increases. What does that mean? Now, to kind of simplify everything, how about us? Think of yourself. What is causing us to accelerate? Move at a constant speed, a curved space-time. What is making us stay on this Earth? So, an Earth's initial motion from the Big Bang is what has it going around the sun, okay? So, Earth is technically traveling in a straight line, but it's warped by the sun's mass. So, it starts curving around the sun, okay? So you take this little sun, this acceleration from the Big Bang, and it starts curving around this mass, okay? So the Earth is going around the sun. Gravity is acceleration. That speed around the sun, that is gravity, but it's the acceleration of it. Now, this point of frame, this point of reference, it does not look like it's going straight. We do not see it as straight. It is going in a circle, but it is going straight when you put it in this timeline continuum, okay? This time versus mass, okay? This large mass has curved our space and time around itself, so it bends time. Gravity actually is bending time. So the Earth is traveling in a circle, when in all reality it is going straight. Now, there's different research theories out there. So there's, again, the string theory, the quantum gravity theory, quantum loop theory. In conclusion, gravity is a manifestation of matter accelerating through warped space-time. And if Earth ever encounters or hits this opposing force and slows, gravity will halt and everything will float off Earth. It's not a force. Gravity is acceleration.